Hey there. So these are the objectives for today's session. First is reducing page faults. So there was a change that I did, which is I shifted from vector to string allocator, and also we'll be adding tail cache. So what I'm talking about. So if we go, if I show you what changes I tried to do. So here are the changes. So I added string allocator. I was using vector initially, and then I moved to what do you say? Yeah, still a keto. But it actually not reduced, increased our latency by around 40 nanoseconds. And I did not know the reason, but then I found out that it most probably is because of page faults. Because I saw so that video isn't released because there was not a lot of things that I covered in the previous one. So I haven't released it, but in that, I found that our code has a lot of page faults compared to rect tops. So I think that is the reason that we'll be fixing, and then we'll be adding a tail cache for some functions. So that's good. So if I just run it for the sake of it to like check what is the score currently, then like 33, and it's 87,000. If I run it again, so it's a similar level 288. Okay. So 288 nanoseconds, 240 nanoseconds, we can round it up to 260 nanoseconds. Yeah, wow, that's correct. So so 260 nanoseconds is the thing. Now uh, let's try reducing page faults. So what happens is that when we were using vector, I'm not really sure. So I'll just check how to use memset because I think when we are using allocate, they are not touching every single space that we have found. So it's actually causing problems when we are running our benchmark because then it's giving page faults every single time, right? Because it's touching that specific part of the memory for the very first time. So I think we can reduce that by using memset, like you can set 0 to every single memset syntax. Well, it's just a scalar, just like memset and see with example. Yeah, yeah. So memset takes in, so it's a pointer, the value, and the size. Okay. So memset uh, BFQ, start, that's the value that we want. So it's 0, and then size of. So till how many bytes do we want it? Well, it's capacity. So let's check. So make clean and make run. Memset was not declared in the scope. Okay. Do I need stdio.h? Is that the reason? Stdio.h. Remove it above. So memset is defining header C string. This is probably fixable by adding C string. Okay. And then these guys tell this ourselves. Make clean, make run. So I think it should be lesser than 260. So I'll consider that a win. But like run 252, and then it's 236, and then it's 238. So I think that's a good win. Yeah, like GG's 250. So now we'll head back to creating tail cache. So size T tail cache. We'll also remove this. Let's do this better. Probably, yeah, I'll do the do the yeah, for now let it be there. So I guess this is fine. Okay, that is bad. Size checks acquires again and again. Hmm. Okay. So first of all, what is happening is okay. So for top is PSC. I have to check like does pop need a check internally or do we just trust the user? DQ the first item of the queue, initial server is non before calling pop. This means that the front must have returned non unpointed before each call to pop requires is thrown non-destructible. Okay, so there's a front check. Okay, maybe we can just call front. There we go. I can add if front not equal to null pointer and remove the empty thing completely. So now no one's using empty, right? Yep. Uh, and then we have employees. So employees calls employees checks if it's filled, and then it just does this. And then there's a push that does employees. Yeah, okay. So let's do some changes and fill. Like so we created a tail cache, right? So you can see head cache we have over here. So where where is tail cache needed? Right? So head cache, let's talk about head cache first. So head cache was needed when we don't need to call head again and again, right? And that is often on the consumer side. On the consumer side, we just need to check like if the element is if some elements are present. So the tail cache is necessary on the producer side. That's why it's so beside head, which is for the consumer, and tail is for the producer. Oh, sorry, my bad. Head is for the producer, tail is for the consumer. The, and then tail cache will be on the producer side. Um, so we can add some checks to in place. So there's a field. I think field is taking some time. We can optimize it maybe. Maybe what we do optimize it. So field is checked. So who calls field? So one, two. So it's a try push in place, try in place, and the function itself. Okay. So it's called on the producer side, right? On the producer side, we have head with us, but we don't need tail again and again. We can just give it a minute. So we have tail cache with us. So what we can do is if um, we don't need to call tail cache again and again, we can just say if head minus tail cache, well, if head minus tail cache is equal to capacity, which is the old value. So if it's equal to capacity, that means it's filled. we can get the new value. So like tail cache will work as if like if head and tail cache are equal, which means there are no elements, but that was for the front, right? So the basis of front was we have to check if there is at least a few elements present, and that means we had to only check, we had to only fetch the latest value from head only and only when we got it as empty. That means front cannot function. So I think this is correct. So we can just do like uh, size t, or maybe again to place tail cache. So tail cache is equal to actually tail dot load stored memory order acquire, right? And then we can check again. So we can check stuff again. So what was the syntax for the head? Yeah, we load it again, and then we do this again. So this is faster. I had checked the previous thing, so this is actually faster. Hmm. We can do it this. I don't mind. And then return head minus tail cache. If head is equal to tail cache, if head is equal to tail cache, then return true. Or if it's not, we return false. So we can limit this. If head is equal to tail cache. No, no, no. Okay, I'm messing up. I'm messing up. I'm so sorry. So I should be instead doing if head minus tail cache is equal to capacity, then return true, else return false. Or I don't even need this, right? We don't even need this. We can just do this. Return x minus tail cache equal to the capacity. With that, we can do that change over here too, right? So worker return t is equal to h. We already did that over here. Okay, we did that over there. So I think this should work. This should give us some boost, but I can't guarantee that stuff. Recording, audible. Okay, that's a boost. The number of operations has increased drastically actually. It's twice again. And if it's twice, that means I'm messing up somewhere. So it's nearly equal. 290 nanoseconds, 209 nanoseconds, so it's lower. It's not faster though. It's doing the number of operations many times. If the number of operations is higher, that means, so let me go into the benchmark. So what benchmark does is that the first test for the number of operations uses in place. So it uses front, pop, and in place. And here it uses again front, in place, pop, and then pop a bunch of times. Okay, not a lot of changes. So did it work? Not really sure. So one more change that I had that I talk about is that Align as doesn't really work how you think it does. So let's check into that. So align as in C++. Align as specifier, C++11. Expression must be an integral constant expression that evaluates to zero or to a valid value for an alignment or exterior alignment. The aligner specifier may be applied to the declaration or definition of a class, the declaration of a non-bit field, okay, whatever. Just tell me what it does, bro. Specify the alignment requirement of a type and an object. That's cool. Every object of your type structure will be aligned to align of this. Align as in C++. So, yeah, that was enough. Yeah, let's look at Stack Overflow. I can't understand align of and align as. A CP reference is unclear, align of returns alignment for its alignment. Number of avoids to add for the next blocks to be aligned. Added size, Stack Overflow blog entries are unclear to you. Alignment is a restriction on which memory positions or values first byte can be stored. Okay. It is needed to improve performance on processors and to permit use of certain instructions that work on only on data with particular alignment. For example, SSE instruction, that is SUMD instructions, need to be aligned to 16 bytes with AVX to 32 bytes, while AVX to 32 bytes. Yeah, okay, fair. Alignment of 16 means that memory address that are multiples of 16 are the only valid addresses. Align as forces alignment to the required number of bytes. You can only align powers of 2. Okay. So align at 16. Okay. Example output is note how many moves you use now. Binary equivalent is this. Every zero is just an extra power of 2. Align as 10,000, 1024, 2 to the power of 10. The other keyword align off is very convenient. You cannot do something like this. Use this and know that this is real. This in reality is more straight than a simple modulus operation. In fact, we know that something aligned to 1024 bytes is really aligned to this. But so to be more precise, align of data set is power of 2 to which something is valid. Starting with an element of 16 will be replaced with an extra address that is a multiple of 16. There may be an implicit pattern from the last use address. There may be an implicit pattern. Okay, so there may be an implicit padding, right? Wait. Does benchmark do a try push check or try in place? No, nothing. So all that is to it is push and place, pop and front, not push. And place. So our in place is cool now. It does a filled check. Filled has tail cache with us. In place here also does the same thing. Try and place front is doing great too, and then filled is doing great too. So there's no problem. Hmm. So I think it's going great. It's okay. So mem set. If I remove this should decrease the performance by a lot. Maybe, maybe not. So make run does this. 129, 340, latency, 209, 209 again, 209, and 209, 249. Okay, fair. 209, 219, okay, fair. So if I add that mem set again, which means we are touching every single memory, so this gives us, so operations has increased maybe, 202, 209. So earlier we were getting like 192,000, 192,000, sorry, 174 and those kind of things. And then we are consistently above 2 lakh, sorry, 218,000. So that is a good indication that it's working, I guess. So 227. These are good numbers, by the way. These are really good numbers. So I think this is it for today's video. Okay. So I think this is it. This is a small enough fix that I've found out. There are some other fixes that I have in mind. The biggest fix that I think is I need to improve the head and tail, like the atomic logic. Not necessarily the atomic logic. So like what it's doing currently is that it's just incrementing. I don't think I like it because it shouldn't be like this. It should be properly like a mod operation. Like not like a mod operation, but currently it's just increasing. It's not taking a new value, but I kept the incrementing logic because I can differentiate whether a, a queue is empty or not. That's why I had to use the head and tail incrementing logic because if they start at the so like let's say they are filled. Let's say your head and cache are completely filled. They still will have head and tail both at zero, both at the same position. So you can't really figure out if they are allocated or not. Then you would have to like keep a flag that says that oh they are completely full and those kind of things. So I like to allocate. Okay, cool. I think that will be a fix for the next video. I think this is a good change for now. Also, one more thing. I think in place we can do one more change, which is like it's cool. It's not that different, you can say. So yeah. So here we are relying completely on the operation. You okay, okay. Yeah, I also had another thing, which is I'll take this by reference, like similar to employees and those kind of things. So I can just do. I was thinking of adding this. So T accept. Although no one is going to use that, but still, do it from our side. So employees during the T also don't do this. If it's a difference. Okay, I need to add. Yeah, I do need to add still mode because T has an identifier now. Like even if it's a R value reference, it still has an identifier, so I need to use still mode. So I think this is cool. Dash mode. Okay. Super. And 35th line. Click run. Um, I don't think there will be a speed increase. It's just another function that I added. And most of the functions are just using L values anyway for push. I don't think anyone's calling push. I think all of them are calling unplace. Okay, so we are near to our goal, which is 1 8, 12 nanoseconds somewhat, 3 and 9 and 12 nanoseconds again, and 2, 9 and 25, which is 16 nanoseconds, and then 238 and 199, and that's 39 nanoseconds. Okay, so we are getting closer. If I run this again, that will be the final thing. 12 nanoseconds. Come on, let's go. 11 and 3. Okay, fine. No, 14 nanoseconds. So that this is a good improvement. Thanks for watching. Okay, I'm Dinesh Avni, and I'm an engineer for fun. Bye.